Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore the techniques and engineering breakthroughs that made modern deep learning trainable. From smarter optimization methods to powerful regularization strategies to the rise of GPU computing.
Welcome. And it's almost impossible to overstate how critical that engineering side is.
Yeah.
We see these incredible models, billions of parameters doing amazing things.
Image generation, translation, all of it.
Exactly. But for a long, long time, even when we knew the basic math, actually training these things was functionally impossible.
That's the real story here, isn't it? It wasn't one single eureka moment. It was more like three separate revolutions happening all at once, which finally unlocked everything.
That's a perfect way to put it. This exploration is really about those three pillars.
Yeah.
Think of it like building a hyper-advanced race car.
Okay.
First, you need the engine, a powerful, adaptable engine. That's optimization. That's how the car or the network actually learns and moves forward.
Then you need the safety systems.
The safety harness, the traction control, everything that keeps that immense power from sending you flying off the track. That's regularization.
And finally, the fuel.
The high-octane fuel and the racetrack itself, the raw power. And that's the hardware acceleration from GPUs. If any one of those fails, the whole system just, it collapses.
So let's start with that engine, with optimization. At the end of the day, training a neural network is just a giant optimization problem, right? You have all these parameters, millions of them.
Billions sometimes.
Billions. And the goal is to just tweak them until the model makes the fewest mistakes possible. And we visualize this whole problem as a loss landscape.
Right. And the standard way to navigate this landscape is with something called gradient-based learning. The analogy everyone uses is perfect for this.
The mountain range.
The mountain range. Imagine you're dropped blindfolded onto a massive, complex mountain range, and your only job is to get to the absolute lowest point, the deepest valley. That valley represents minimum error.
But you're blindfolded, so you can't see the map. You can only feel the ground right under your feet.
Exactly. The gradient is just the mathematical way of telling you which direction is the steepest uphill.
So you just do the opposite.
You do the exact opposite. You take a step downhill. The size of that step, that's your learning rate. This whole process is called gradient descent.
Now, ideally, to find the true slope of the mountain, you'd average out the slope from every single point on the mountain.
That would be batch gradient descent, using the entire data set.
But if your data set has billions of points, that's computationally, well, impossible.
You never even take a single step. So that led to the first compromise. Stochastic gradient descent, or SGD. Stochastic just means random.
So instead of the whole data set,
You use just one single data point at a time to guess the slope. It's incredibly fast, but your path down the mountain becomes really erratic. You're staggering all over the
it
place.
sounds horribly inefficient, like you might never get to the bottom.
It can be very, very slow to converge. So the practical solution, the one everyone uses, is mini-batch SGD.
The middle ground.
The perfect middle ground. Use a small sample, maybe 32, 64, up to 512 data points to get a much more stable estimate of the gradient. It's efficient, and crucially, it lets us use modern hardware. We can process all 64 of those samples in parallel.
Okay, so that makes sense. A mini batch gives you a pretty good sense of which way is downhill, but it's not perfect. It's a little bit noisy.
And that noise is a key theme we're going to keep coming back to. Sometimes noise is a good thing.
A feature, not a bug.
Right. But even with this, early attempts to build really deep networks, with dozens of layers, they just hit a brick wall, a huge one. The vanishing gradient problem.
This is where the engine just completely seizes up.
Completely. Imagine the learning signal, the gradient, has to travel backwards from the final layer where you calculate the error all the way back to the very first layer. Back in the day, the activation functions people used, like sigmoid, had a nasty mathematical property. As the gradient passed through each layer, it got multiplied by a very small number.
And a small number times a small number times another small number.
Very quickly becomes basically zero. By the time the signal got to those crucial first few layers, the ones that learn basic things like edges and colors, there was nothing left. No signal.
So they just stopped learning.
They stopped learning entirely. They were frozen. This one problem basically ensured that deep learning was stuck being shallow learning for years.
So if the gradient signal itself was vanishing or just too noisy to trust completely, we needed a smarter way to move, not just based on the slope right now.
Right. And that's where momentum comes in. It's a really intuitive idea. If you're rolling a ball down a hill, it doesn't just stop and change direction instantly. It has inertia.
It builds up speed.
It builds up speed. So momentum in optimization does the same thing. It adds a fraction of the previous update to the current one.
Yeah.
It helps smooth out the little jitters from the mini batches and keeps you moving in the general downhill direction.
So you don't get distracted by one noisy mini batch that tells you to go sideways for a second.
Exactly. You look at the broader trend. And what was amazing was that simple SGD, when you combined it with momentum, especially a clever version called Nesterov's accelerated gradient, or NAG, it worked incredibly well.
What's special about Nesterov?
It's a look-ahead step. Instead of calculating the gradient right where you are, you first make a jump based on your momentum, and then you calculate the gradient from that new spot. It helps you anticipate the curve and slow down at the right time. It was a huge deal.
That is clever, but it's still using one single learning rate for every single parameter in the entire network, right?
Yes, one universal speed limit. And that was the next big realization. Why should they all be the same?
Right. Some parameters might be for really common features. They get updated all the time. Others might be for something super rare.
And they barely ever get a signal. It's like having a highway and a winding mountain path, but forcing everyone to drive at 30 miles per hour. It's inefficient.
So we needed personalized speed limits.
Adaptive step sizes. An early attempt was Adigrad. It worked by keeping a running sum of the squared gradients for each parameter. If a parameter got lots of updates, its learning rate would get smaller and smaller.
Which sounds good for those rare parameters. They would keep a high learning rate.
It was brilliant for things with sparse data, like natural language processing, where most words are rare. But there was a fatal flaw.
The word sum implies it just keeps growing.
It never forgets. The sum only ever increases, so eventually the learning rates for all parameters would just plummet toward zero, and training would grind to a halt, often way too early.
So we needed a way to have a memory, but a short-term one.
That's the key innovation of RMSProp. Instead of an ever-growing sum, it uses an exponential moving average of the squared gradients. This means older gradients gradually fade in importance.
So the learning rate is based on recent history, not ancient history.
Precisely. It keeps the learning relevant and allows training to continue effectively. And this all sort of culminates in what is now the default optimizer for most people, ADAM.
Adaptive moment estimation.
ADAM is so elegant because it just combines the best of both worlds. It keeps two separate moving averages for every parameter.
Okay, what are they?
It tracks the average of the gradient itself. That's the first moment, which is like momentum. And it tracks the average of the squared gradient, the second moment, which is like RMSProp.
So it has the inertia from momentum and the personalized speed control from RMSProp.
All in one package. It dynamically calculates an individual learning rate for every single parameter. And it adds a clever little correction for the start of training when the averages are still biased towards zero. It's robust, it works well on a huge range of problems. It's the tool you reach for first.
The power of these adaptive methods really highlights just how insane this loss landscape must be.
It's a nightmare terrain. It's not a simple bowl, it's non-convex. It's full of these little local minima, which are valleys, but not the deepest one.
But the bigger problem is saddle points, right?
A much bigger problem. A saddle point is like a mountain pass. It goes down in some directions, but up in others. If you land right in the middle, the gradient, the slope, is basically zero in all directions.
So the optimizer thinks it's found a nice flat minimum.
It thinks it's done, gets stuck, when really it just needs a tiny push to start rolling down to a much deeper valley.
So anything that can give it that push is a good thing, which I guess brings us to something that sounds completely backwards: cyclical learning rates.
CLR was so counterintuitive. For decades, the wisdom was you always decrease your learning rate over time. Start fast, finish slow.
Sure, that makes sense. You take big steps at first, then smaller, more careful steps as you get closer to the bottom.
CLR throws that out the window. It says you should cyclically vary your learning rate between a minimum and a maximum. Go up, then down in a little triangle wave.
But why would you ever want to increase the learning rate? That feels like you're just inviting chaos and making the error worse.
In the short term, you are. But that temporary increase acts like a jolt of energy. It's powerful enough to blast the optimizer out of those tricky saddle points or across long, flat plateaus where it might have gotten stuck.
So it's an escape mechanism.
A powerful one. And it often finds better solutions and removes the need to spend weeks manually tuning a learning rate schedule.
Okay, so we know how to move and we know how to get unstuck. But we touched on something earlier, that the noise from small mini batches is somehow good. This leads to this idea of the generalization gap.
This is one of the most fascinating insights in modern deep learning. When we use small batches, the gradient we calculate is noisy. That constant jittering actually prevents the optimizer from settling into just any minimum. It forces it to find flat minimizers.
And a flat minimizer is a really wide valley.
A broad, wide basin. The key property is that if you move around a little bit inside that basin, the error doesn't change much. This makes the solution incredibly robust. It generalizes well to new data.
Because small changes in the input won't suddenly push you up a steep cliff of high error.
Exactly. But now think about what happens with really large batches, thousands of samples.
You lose the noise. The gradient becomes very, very accurate.
And that super accurate gradient leads the optimizer to find sharp minimizers. These are incredibly narrow, deep ravines. The model is perfect on the training data, but if you give it new data that's just slightly different,
The error shoots up.
it spikes. And that's the generalization gap. You can see a 5% drop in accuracy just by changing the batch size. It's huge.
But we want to use large batches for hardware efficiency, so how do you solve that?
People came up with some very clever tricks. One is a learning rate warm-up. If you use a huge batch, you need a huge learning rate. But if you start with that, the model just explodes. So you start with a tiny learning rate and slowly ramp it up over the first few epochs.
You ease into it.
You ease into it. And for really massive scales, you have algorithms like large layer-wise adaptive rate scaling, which calculates a custom learning rate for each layer of the network. These techniques let us train with massive batches without sacrificing performance. It all comes back to managing or sometimes even creating noise.
Okay, so we've built a very sophisticated engine and we know how to steer it. Now we need the safety harness. Regularization. This is all about making sure that powerful engine is actually learning useful things, not just memorizing the map.
And the need for this is born from the absolutely insane capacity of modern networks. They're just too powerful, too expressive.
What's the proof of that?
There's this landmark experiment. Researchers took a state-of-the-art image recognition network and trained it on a data set where they replaced all the images with complete random noise. Just static.
Garbage in.
Total garbage in. And even crazier, they took another data set, kept the real images, but just shuffled all the labels randomly. So a picture of a cat was labeled car, a dog was airplane, and so on.
Then what happened?
The networks achieved 0% training error.
Wait, they perfectly learned to classify random noise.
They perfectly memorized it. They didn't learn a single useful feature, of course, but they had enough capacity to just create a perfect lookup table for the entire garbage data set.
That is the definition of overfitting.
It's the ultimate proof. The theory is that as soon as your number of parameters is bigger than your number of data points, which is almost always true now, the network has what's called perfect finite sample expressivity. It can fit anything.
So regularization is the set of techniques we use to force it away from memorization and towards generalization.
Exactly. It's the set of constraints that makes learning meaningful.
And before we even get to the explicit techniques, maybe the most important one is an internal stabilizer, batch normalization.
Batch norm was and is a revolution. It solved a problem called internal covariance shift.
Which sounds complicated.
The idea is simple. As you train, the weights in the first layer update. That changes the data distribution that the second layer sees. Then the second layer updates, which changes what the third layer sees.
So every layer is trying to learn on constantly shifting ground.
It's total chaos. Batch norm solves this by just inserting a normalization step between layers. For every mini batch, it calculates the mean and variance of what's coming into a layer and rescales it.
So every layer gets a nice, stable, predictable input distribution to work with.
And the results were just staggering. It stabilized training so much you could use way higher learning rates. Models train faster. In some cases, a model with batch norm got the same accuracy with 14 times fewer training steps.
14 times?
It was a massive leap forward. It also acts as a regularizer itself, often making other techniques less necessary. It was a true game changer.
But batch norm depends on the statistics of the mini batch, right?
Yeah.
What if your batch size is 1, or you're working with sequences in an RNN?
Great question. That's where layer normalization comes in. Instead of normalizing across the batch, Layer norm normalizes across the features within a single example. It's independent of the batch size.
So it's more flexible.
Much more. And it's essential for models like RNNs and, later on, transformers. It's the same core idea, just applied along a different dimension.
Okay, so once the network is internally stable, we can start adding explicit regularizers. The classic one everyone learns about is dropout.
Dropout is just such a clever, beautiful idea. During training, for every mini-batch, you just randomly turn off a fraction of the neurons in a layer. Just set their output to 0.
How on earth does randomly breaking parts of your network make it better?
It forces teamwork. Imagine you're a neuron. You know that at any moment, your neighbors might just disappear. So you can't afford to rely too heavily on any single one of them for information.
You can't have specialists.
You can't. It prevents this thing called co-adaptation. The network is forced to learn redundant, distributed representations. The knowledge gets spread out across the whole layer, making it much more robust.
So for each mini-batch, you're actually training a slightly different, smaller network.
That's the key insight. You're effectively training a huge implicit ensemble of many smaller, weaker networks all at once. The final model is the average of all of them, and it generalizes far better.
That's brilliant. We can also regularize by messing with the data itself. There's classic data augmentation like flipping and rotating images, but then there's something much stranger called mixup.
Mixup is wonderful because it's data agnostic. It works on anything. It trains the model on virtual examples that don't actually exist in the dataset.
How does it create one?
It's shockingly simple. It just takes 2 random examples from your training set, say a picture of a cat and a picture of a dog.
Okay.
It then literally blends them together. It creates a new image that is, say, 70% the pixels of the cat image and 30% the pixels of the dog image. And crucially, the label for this new Franken image is also blended, 70% cat, 30% dog.
So you're forcing the model to understand the space between the clear-cut examples.
You're forcing it to behave linearly. You're telling the model, if something looks 70% like a cat and 30% like a dog, your output better be close to 70-30. It smooths out the decision boundaries between classes and makes the model much more stable.
Now, there's a really subtle but important point that connects optimization back to regularization, and that's the difference between L2 regularization and weight decay.
Yes, this is deep in the weeds, but it's so important. It explains why Adam, for a while, seemed to generalize worse than good old SGD with momentum.
So what's the difference? They sound the same.
For standard SGD, they are mathematically identical. L2 regularization adds a penalty to your loss function to keep the weight small. Weight decay is an action you take after the gradient update where you just shrink the weights a tiny bit towards 0.
So if they're the same for SGD, why are they different for Adam?
Because of the adaptive learning rates. Adam scales the update for each weight individually. When you use L2 regularization, that penalty term gets tangled up in Adam's adaptive scaling. The regularization effect gets magnified for some weights and basically canceled out for others.
So Adam was accidentally breaking its own regularizer.
It was defeating the purpose. This is why Adam would often converge to those sharp minimizers we talked about. The solution was an algorithm called Adam W.
The W is for weight decay.
Exactly. It decouples the two. The weight decay is applied as a completely separate step after the main Adam update, so it isn't affected by the adaptive scaling. This simple fix dramatically improved Adam's generalization performance. It's a great story of how a subtle implementation detail can have a huge impact.
And one last technique here, label smoothing, which tackles the model's tendency to become overconfident.
Right. A normal model is trained to be 100% certain. If the image is a cat, the target probability for cat is 1.0. And it's 0.0 for everything else. This makes the model very rigid.
It doesn't allow for any doubt.
And that can hurt generalization. Label smoothing just says, let's relax that target a little. Instead of 1.0, maybe the target for cat is 0.9. And we'll spread that remaining 0.1 of probability mass evenly across all the other wrong classes.
So you're telling the model, be pretty sure it's a cat, but don't be absolutely certain.
Precisely. It regularizes the model, prevents the internal values from getting too large, and leads to better calibrated, more adaptable models.
Okay. We have the smart engine, we have the safety harness. None of it matters if you don't have the fuel, the brute force power to actually run these billions of calculations. This brings us to the third pillar, GPUs.
Absolutely. The need for them was born out of pure necessity. Central processing units, CPUs, they're too slow.
Why? What's the architectural difference?
A CPU is a master of complexity. It's designed to run your operating system, handle intricate logic, do one or two very complicated things at a time very fast. But deep learning is the opposite. It's not complex. It's a massive amount of very, very simple work.
Mostly matrix multiplications.
Billions and billions of them. And that kind of work is what we call inherently parallelizable. A GPU, which was born to render graphics for video games, is a many-core architecture. A chip, like an NVIDIA V100, has thousands of tiny, simple cores.
So instead of a few genius cores, you have thousands of worker cores.
A perfect analogy. They operate on a model called SIMNT, single instruction, multiple thread.
What does that mean in simple terms?
I mean, the GPU issues one single command, like multiply these two numbers, and thousands of its cores all execute that exact same command at the exact same time, but on different little pieces of data. It's a massively parallel assembly line.
And that's just a much better fit for the math of neural networks.
It's an exponentially better fit, and more energy efficient, too. The GPU is the undisputed workhorse, but the hardware alone wasn't enough. The software ecosystem built on top of it was just as important.
You're talking about CUDA and cuDNN.
Exactly. CUDA was NVIDIA's programming language that suddenly made it much easier for researchers to actually write code for these weird parallel chips. But the real linchpin for deep learning was cuDNN.
And what is that specifically?
It's a library of hand-optimized, super-fast primitives for neural network operations. Things like convolution, pooling, the fundamental building blocks. So when a framework like TensorFlow or PyTorch needs to do a convolution, it doesn't have to figure it out. It just calls the hyper-optimized cuDNN routine.
So it's a standardized library of speed.
It is. It made sure everyone's code ran as fast as humanly possible on the hardware. It was a massive accelerator for the whole field.
But programming for a GPU is a different beast than for a CPU. You have to be aware of the hardware.
Very aware. For instance, a huge performance killer on GPUs is something called branch divergence.
Okay.
GPUs execute threads in groups called warps. All 32 threads in a warp execute the same instruction. If your code hits an if-else statement, and some threads need to go down the if path and others need to go down the else path,
It has to split up.
the hardware can't do that. So it has to run the if block for the first group, then turn around and run the else block for the second group. It serializes the work. It completely destroys your parallelism for that moment.
So you have to write code that avoids that.
You have to be very clever. And another example is how we handle convolutions. General matrix multiplication, or GMM, is the single most optimized routine in all of scientific computing. GPUs are incredible at it.
But a convolution isn't technically a matrix multiplication.
Not directly. So what the libraries do is a trick called convolution lowering. They take the input data and rearrange it, often duplicating parts of it, to transform the convolution operation into one gigantic GMM problem.
So they can use that hyper-optimized JMM code.
Exactly. But it comes at a cost. A huge memory overhead to store that big temporary matrix. And that's where you start running into the limits of your GPU's memory.
I remember this battle well, trying to fit a big model like VGG16, which needed something like 28 gigs of memory, onto a graphics card that only had 12.
And that struggle led to some really clever solutions. One was just offloading data. You could move some of the intermediate results, the activations, off the GPU and onto the main system RAM, and then pull them back when you needed them for the backward pass.
Slow because of the transfer, but it lets you run.
It lets you run. Another trick was recomputation. Instead of storing the output of a layer, which might be huge, you just throw it away. Then during the backward pass, when you need it again, you just run the forward pass for that one layer to recalculate it on the fly.
So you trade compute time for memory space?
It's a classic engineering trade-off, and it could cut memory usage in half for some layers, which made all the difference.
And when one GPU just isn't enough, no matter how many tricks you use, you have to scale out to a whole cluster.
Right, distributed training. There are two main models for this. The first is the parameter server.
How does that work?
You have a central server node, the PS, that holds the master copy of the model's weights. All the other worker GPUs compute their gradients and send them to the PS. The PS averages them, updates the weights, and sends the new weights back out.
That central server sounds like a bottleneck.
It is. Once you have hundreds of workers, the PS can't keep up with all the communication. That led to the other approach, which is all reduce.
All reduce is decentralized.
It's a collective operation. There is no central server. The workers talk directly to each other, passing their gradients around in a ring or some other pattern until every worker has the sum of all the gradients. It's much more scalable, but it requires everyone to be in sync.
But maybe the single biggest breakthrough for training at scale was mixed precision.
Oh, absolutely. This was a purely pragmatic engineering triumph. Modern GPUs have special hardware called tensor cores that are insanely fast at doing math with 16 bits floating point numbers, FP16, instead of the standard 32-bit FP32.
So if you can use FP16, you basically have your memory usage and get a massive speed up from the tensor cores. What's the catch?
The catch is that 16 bits gives you much less precision. Tiny gradient values, which are very important for learning, can become so small that they get rounded down to 0. This is called underflow. The signal just vanishes.
So you lose the update entirely.
Which cripples training. The solution is the mixed precision workflow. It's brilliant.
How does it work?
You keep a master copy of all your weights in high precision FP32. Then you do all the fast, heavy lifting math, the matrix multiplications, in low precision FP16.
When you get the gradients back, you convert them back to FP32 before you apply them to your master weights.
So the weight updates themselves are still precise. But how do you stop the gradients from vanishing when they're still in FP16?
With a simple trick called loss scaling. Before you start the backward pass, you just multiply your loss value by a big number, say 1024. This scales up all the resulting gradients, pushing them up into a range where they won't underflow in FP16.
And then you just divide them back down later. You divide them back down before you apply them to the master weights. This combination, FP32 masters, FP16 compute, and loss scaling, is what made training truly massive models like transformers practical.
And even with all that, the memory needed for the optimizer itself, like Atom, which triples the memory requirements, is still a problem.
It's a final frontier, and that's where state-of-the-art techniques like Zero, the zero redundancy optimizer, come in. Zero is incredibly smart. It partitions not just the data, but the model state, the parameters, the gradients, and the optimizer states across all the GPUs in the cluster.
So no single GPU has to hold the whole model anymore.
No GPU holds the whole thing. It dramatically cuts down on memory redundancy and allows for training models at a scale that was just unthinkable a few years ago.
Listening to all of this, it's so clear that the deep learning revolution wasn't just one thing. It was this perfect storm, this convergence of all three pillars at once.
It had to be. You can't separate them. Imagine trying to train a big model today without batch normalization. It would be so unstable it would never converge.
And even if it did, without proper regularization like decoupled weight decay, it would just overfit horribly. It would get a great score on the training set and be useless in the real world.
Absolutely. The safety harness wouldn't hold. And most of all, even if you have the perfect algorithms, if every single experiment took 2 years to run on the CPU instead of 2 days on a GPU,
you'd never make any progress. The iteration speed just wouldn't be there.
The ability to run these massive computations, accelerated by GPUs and cuDNN and mixed precision, is what allowed researchers to even explore the big architectures like ResNet and transformers that led to the big breakthroughs.
It really highlights that progress in AI today isn't just about a new model diagram. It's just as much about hardcore engineering, making data move faster, solving numerical stability, managing memory across 1,000 machines.
And that's really the foundation for everything that comes next. Understanding how we optimize, regularize, and accelerate is the context you need to really appreciate the challenges and triumphs behind CNNs for vision, RNNs for language, and the giant foundation models we have today.
It's the bedrock, and it makes you wonder what the next big leap will be. Maybe not a new architecture, but a small tweak to an optimizer or a new hardware trick that unlocks another order of magnitude in scale.
It's entirely possible. The engineering is just as important as the theory.
Sometimes the biggest leaps in capability come not just from revolutionary ideas, but from refining the underlying mechanics of how we learn, how we prevent confusion, and how we accelerate the sheer labor of computation. Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.